Hello dear students. Today we are going to discuss about another new topic of determinant. Today's topic is adjoint of a matrix and inverse of a matrix. These are the two topics we are going to discuss in this class. In our previous class we had a discussion about finding the minus and cofactors. We have seen how to find the minus, how to find the cofactors, and what is the relation between minus and cofactors. We have seen in our previous class, and I told you that the minus and cofactors are useful for finding the inverse of a matrix. So minus are possible only for a square matrix, that too where the order is greater than or equal to 2. When you have a square matrix 2 by 2, 3 by 3, 4 by 4, etc. For such kind of matrices only we have to find minus. So minus we need to calculate for every element presenting in the determinant. If it is a 3 by 3 square matrix or 3 by 3 determinant, we have 9 elements. For every element we can find the minus. So when we are able to find minus for every element, automatically we can find the cofactors for each and every element presented in the determinant. Now the continuity of the minus and cofactors, we have another concept is adjoint of a matrix. So what is the meaning of adjoint of a matrix? Let us see the definition. The adjoint of a square matrix. So determinant concept, when we have started, throughout the chapter we are discussing only a square matrix. There is no question of rectangular matrix because determinant is possible only for a square matrix. That's why throughout this chapter, whenever there is a matrix, the matrix must be a square matrix. So there is no confusion whether the matrix is square or rectangular. Determinant means it must be a square matrix. It is not at all a rectangular matrix. So here also when we are talking about adjoint of a matrix, so the matrix must be a square matrix. A is equal to Aij n by n means n rows and n columns. We can say that the order of the matrix is n. Is defined as the transpose of the matrix. What we need to find? Transpose of the matrix. For what we need to find transpose? For this matrix. What is this? Capital Aij n by n. So what is the meaning of capital Aij? Yesterday I told you that minus are denoted with Mij, cofactors are denoted with Aij. So Mij indicates minus, Aij indicates cofactors. This we know that. So here Aij indicates the cofactors. So transpose of the matrix Aij, where Aij is the cofactor of the element Aij. So here there is a matrix A. If it is 2 by 2 square matrix, we have 4 elements. All the 4 elements we should find the cofactors, then we should have a matrix. That transpose is nothing but called adjoint of the matrix. So first we need to find cofactors for every element. With all the cofactors we have one matrix. That matrix is called cofactors matrix. So after finding the cofactor matrix, now we have to transpose it. So transpose of a cofactor matrix is nothing but called adjoint of the matrix A. So the adjoint of the matrix A is always denoted by by ABJ, adjoint A. So ABJ A is nothing but called adjoint of the matrix A. So this is the definition about adjoint of a matrix. So very clear, we should have a square matrix. For example, when we have a 2 by 2 square matrix, in 2 by 2 square matrix we have 4 elements. For all the 4 elements we should find the cofactors. With that cofactors we will have a matrix. The transpose of that matrix is nothing but called adjoint of the given matrix. Here we have a concept to understand what is adjoint. Let us see here. Let capital A. It is a 3 by 3 square matrix. So we have total 9 elements. For 9 elements we should find the cofactors. For A11, when we find cofactor, it is represented as capital A11. A12, its cofactor is capital A12. A13, its cofactor is capital A13. A21, its cofactor is capital A21. A22, its cofactor is capital A22. A23, its cofactor is capital A23. A31, its cofactor is capital A31. A32, its cofactor is capital A32. A33, its cofactor is capital A33. So with all these cofactors, we are having another matrix, which is nothing but called cofactor matrix. Which is nothing but called what? Cofactor matrix. Once we know that cofactor matrix, then we can find adjoint of A. How to find adjoint of A? By transpose of the cofactor matrix. So for this we are doing transpose. As we know that transpose means what? Interchanging rows into columns into rows. So here whatever the rows we have, all the rows are converted into columns. So you can observe it. Now the transpose of this cofactor matrix is A11, A12, A13. Here this is the first row. Now the first row became first column. Now what is the second row? A21, A22, A23. The second row became second column. A21, A22, A23. What is the third row? A31, A32, A33. Now it became column 3. A31, A32, A33. So this is cofactor matrix. Transpose of this cofactor matrix is nothing but called adjoint of a given matrix. So this is about adjoint of A. What is the importance of adjoint of A? Why we need to calculate this adjoint of A means whenever we need to find inverse of a matrix, we require adjoint of A. Let us see how it is required and how to find the adjoint of A matrices. Now we see, so that by observing one example problem, you can have more clarity regarding this concept. Let us see one example based on the adjoint of A. Here we have one example regarding adjoint of a matrix. Now let us see how to find adjoint of a given matrix. We have an example number 23 from page number 127. What is the question given for us? Find adjoint A for capital A is equal to 2, 3, 1, 4. So 2, 3, 1, 4 is a square matrix of order 2. Now let us see. Given this is the matrix given. Now directly we are finding the cofactors. Without finding minus, directly we can find cofactors also. How? First, when we talk about 2. So the position of 2 is first row of first column. So its cofactor is capital A 1 1. As we know that cofactor formula, yesterday in our previous class we have seen Aij is equal to minus 1 power I plus j into Mij. This is the formula for cofactors. Now directly we are finding it. A11 is equal to minus 1 power 1 plus 1. How to find minor? Leaving the respective row and respective column. When we are talking about 2, leaving the column and leaving the row. Now what is the element we have? 4. So the 4 comes here. So minus 1 power 1 plus 1 2. When power is even, negative will convert into positive. Finally we have the answer 4. Now A12. So I am talking about 3. The position of 3 is first row, second column. So capital A 1 2. So as for the formula, minus 1 power I plus j means minus 1 power 1 plus 2. And leaving the respective row and column, we have the element 1. So the 1 comes here. 1 plus 2, 3, odd number. So that you have minus 1. Minus 1 into 1 gives us minus 1. Now come for 1. What is the position of the element 1? So here the 1 is located in second row of first column, means capital A to 1. Again by using the formula, minus 1 power I plus j. So minus 1 power 2 plus 1. And when we are talking about 1, leaving the respective column and row, now we are able to see the element 3. So the 3 comes here. Again 2 plus 1 is 3, odd number. So you have minus 1 into 3 gives us minus 3. Now in the last element 4. When we are talking about 4, the position of the 4 is second row, second column. So capital A 2 2. Again as for the formula, minus 1 power 2 plus 2. When we are talking about 4, leaving the respective row and respective column. Now we have the element 2. The 2 comes here. So 2 plus 2 is 4. 4 is even number. Minus becomes plus. So we have 2. 2 is the answer. Now what are the cofactors we have? The first cofactor is 4. The second cofactor is minus 1. The third cofactor is minus 3. And the fourth cofactor is 2. Now we have cofactors matrix. Now cofactors matrix A is equal to. Now the cofactors we write here. 4, minus 1, minus 3, 2. This is about cofactor matrix. So with all cofactors we have a matrix. Now what is adjoint of a matrix? Now we are talking about adjoint. So adjoint is nothing but transposition. What we need to transpose here? The cofactor matrix we need to transpose. Means interchanging rows into columns. Let us interchange. So adjoint of A is equal to, this is the row 1. The row 1 will converted as, so here 4 minus 1 minus 3 2 I am talking about transpose. Now the row 1, this is the row 1 converted as column 1, row 2 converted as column 2. So finally we have the adjoint matrix A is 4 minus 3 minus 1 2. This is nothing but called adjoint of A. So very easy. What we are doing first? Finding cofactors. With all cofactors we are forming a matrix. That matrix we are taking transpose. Just 2 steps. Step 1, finding of cofactors. Step 2, framing a cofactor matrix. Step 3, transposition of that. So by solving these 3 simple steps, we can find adjoint of the matrix A. This is about the concept of adjoint of A. And here we can observe a simple technique for finding the adjoint of A. Only for 2 by 2 square matrix, not for 3 by 3 square matrix. Whenever you have a 2 by 2 square matrix, In a simple way, we can find adjoint of. Let me explain. Just observe these two matrices, how they are. 2, 3, 1, 4. 4 minus 3 minus 1. What we have observed here? 3 and 1. Here 3 is positive, 1 is positive. What happened here? Signs are changing. And let us come to here. 2 and 4. These two are interchanged. Means 4, 2. Means whenever you have a matrix A, B, C, D. For this, the adjoint of A very easily we can find. What way we can find, sir? These are the principal diagonal elements. Principal diagonal elements. Interchange. So now we need to interchange. So principal diagonal element has to interchange. Means I have D and I have A. So interchange these two principal diagonal elements. Now another diagonal elements we have. These are the elements. Change of signs. Change of signs. Here B is which one? Positive one. So I can take minus. C is which one? Again it is positive. I can change minus. So this is nothing but called adjoint of A. So this technique is only for a 2 by 2 square matrix. It is not applicable for 3 by 3 square matrix. So whenever you have a 2 by 2 square matrix, the principal diagonal element has to interchange. Another diagonal elements, we have to change the signs. In this technique, let us see the problem. Now I have A, 2, 3, 1, 4. Now I want adjoint of A. Very simple. Interchanging these two elements means 4, 2. Changing of signs minus 3, minus 2. So that's all. Now you observe the answer. Here we have the answer 4 minus 3 minus 1, 2. Here also we have the answer 4 minus 3 minus 1, 2. So it is a simple technique. This technique is applicable only for a 2 by 2 square matrix. It is not applicable for a 3 by 3 square matrix. This is about how to find adjoint of a given matrix. An important theorem 1. What is the theorem? If A be any given square matrix of order n, then A into adjoint of A is equal to adjoint of A into A is equal to det A into I. Here I is nothing but identity matrix of order n. So whenever we have a square matrix, the square matrix is multiplied with its adjoint matrix. The answer comes for us det A into I. That is our theorem 1. Now, why it happened and how it happened? Let us see here. When there is a matrix A, so we have the elements A11, A12, A13, A21, A22, A23, A31, A32 and A33. We have 9 elements. For all 9 elements we can find cofactors and its transpose we can get adjoint matrix, everything we know. Now the adjoint matrix is A11, A12, A13, A21, A22, A23, A31, A32, A33. This is our adjoint matrix. Now I need to multiply these two. A into adjoint of A. It is a 3 by 3 square matrix and it is a 3 by 3 square matrix. Both can multiply. You know how to multiply. So first row 1 will multiply with column 1. Again multiply with column 2. and it multiply with column 3. So A11 into capital A11 plus A12 into capital A12 plus A13 into capital A13. This is about row 1 into column 1. We are getting this value by multiplying row 1 into column 1. Now again, row 1 into column 2. A11 into A21 plus A12 into A22 plus A13 into A23. Here we have. This is, we are getting row 1 into column 2. This we are getting row 1 into column 1. Row 1 into column 2. Row 1 into column 3. So, row 1 is multiplied with column 1, multiplied with column 2, multiplied with column 1. Similarly, row 2 into column 1. Row 2 into column 2. Row 2 into column 3. So, this is row 2 into column 1, row 2 into column 2, row 2 into column 3. Next, with row 3, we should multiply column 1. Row 3 into column 2. Row 3 into column 3. This is, we are getting row 1 into column 1. Sorry, row 3 into column 1, row 3 into column 2, row 3 into column 3. Anyway, we know how to multiply the matrices. We have seen in chapter number 3. Now, once if you observe this product, now A11, the number is multiplied with its cofactor. A11, what is its cofactor? Capital A11. So number is multiplied with its cofactor plus A12. A12 is multiplied with its cofactor, capital A12. A13, number is multiplied with its cofactor, capital A13. So here the underlined value is nothing but number is multiplied by its cofactors. Here also when we observe A21 is multiplied with its cofactor, A22 is also multiplied with its cofactor, A23 is also multiplied with its cofactor. Now, A31 is multiplied with its cofactor, A32 is also multiplied with its cofactor, A33 is also multiplied with its cofactor. Whenever an element is multiplied with its cofactor and the sum gets us that A. So here the underlying values, all we are getting the sum. It is a sum and it is also a sum and it is also a sum. How you are getting that sum? The sum is nothing but product of the elements with its respective cofactors. So whenever the sum gets by multiplying a number with its cofactor is nothing but called determinant. Is nothing but called determinant. So this entire sum gives us that A. This entire sum is also gives us that A. This entire sum is also gives us that A. So all principal diagonal elements we get that A, that A, that A. Then what about remainder? In our previous class, we had a concept. When the elements of any row or column are multiplied with other cofactors of any row or any column. Row 1 elements are multiplied with row 2 elements of cofactors. Row 1 elements are multiplied with cofactors of row 2 elements and the sum gets us 0. In our previous video, we have seen that example also. So we have an example problem. There is a 3 by 3 square matrix. Find all the cofactors and they asked to show that answer is also 0. By using that concept, here A11, A12, A13. These are the row 1 elements. A21, A22, A23. These are the cofactors of row 2. So row 1 elements are multiplied with other row of cofactors. So this entire product gets us 0. Similarly, here A11, A12, A13. These are also A11, A12, A13. These are also row 1 elements are multiplied with row 3 cofactors. So that this value also gets 0. Like that, remaining all values will get zeros. Here only two concepts. When the same row elements are multiplied with its cofactors, the sum will get determinant of the matrix. If one row elements are multiplied with other row cofactors, the answer gets us 0. That same concept we are applying here. By applying that concept here, we have det A 0, 0, 0, det A 0, 0, 0, det A. Det A can be taken common. Now by taking det A common, we have 1, 0, 0, 0, 1, 0, 0, 0, 1. Here 1, 0, 0, 0, 1, 0, 0, 0, 1 is nothing but identity matrix. So we have det A into I. Finally, the product of A and adjoint of A, we got det A into I. So this we have. Similarly, we can get this also. So for any square matrix A, the product of A and its adjoint of A, or adjoint of A and A, the product gets us det A into I. This is the concept of theorem number 1. Now, we have another important type of a matrix. What is that? Singular matrix. So, what is the meaning of singular matrix? We have seen many types of matrices earlier. Square matrix, rectangular matrix, row matrix, column matrix, transpose of the matrix, symmetric matrix, skew symmetric matrix. Like that, there are many types of matrices. Now, this is another kind of matrix which is called singular matrix. What is the meaning of singular matrix? A square matrix A is said to be singular if det A is equal to 0. So, whose determinant value is 0, then the matrix is called singular matrix. Once again, whose determinant value is 0 is called a singular matrix. So, we don't know whether the given matrix is singular or non-singular. They will give a matrix, just we follow the procedure of determinant. Finally, we observe the value, whether the answer is 0 or not. When the answer is 0, we call it is a singular matrix. When the answer is not equal to 0, then it is called non-singular. We have two types of matrix: singular matrix, non-singular matrix. Singular matrix means whose determinant is equal to 0. Non-singular matrix means whose determinant is not equal to 0. So here we have two examples. Example 1, we have a square matrix 1, 4, 2, 8. When we find the determinant, so det A is equal to det 1, 4, 2, 8. 1 8 is 8 minus 2 4 is 8 is equal to 0. Here I got the determinant 0, so that it is called singular matrix. Now coming to the another example. Here we have a matrix 1, 4, 3, 8. When we calculate the determinant, that A is equal to that 1, 4, 3, 8. 1 8 is 8 minus 3 4 is 12. 8 minus 12 is minus 4, which is not equal to 0. So that is called non-singular matrix. So this is about the concept of singular and non-singular. What is the importance of singular and non-singular? Whenever you need to find the inverse of a matrix, first we need to check whether the given matrix is singular or non-singular matrix. Whenever you have a singular matrix, inverse does not exist. When there is a singular matrix, inverse is not possible. When the matrix is non-singular, then we can find the A inverse. So for singular matrix, inverse does not exist. For non-singular matrix, inverse exists. So in our next concept, we are going to find the inverse. So while finding the inverse of a matrix, first we check whether the given matrix is singular or non-singular. Then we proceed the finding of inverse of a given matrix. Now we have three important theorems. Just now we have seen theorem 1. Now let me explain theorem 2, theorem 3, theorem 4. Theorem 2. What theorem 2 says? If A and B are non-singular matrices of the same order, then A into B and B into A are also non-singular matrices of the same order. Means that here A and B are non-singular matrices. So what is the meaning of non-singular? Non-singular means when the determinant is equal to 0 is called singular. Determinant is not equal to 0 is called non-singular. Means that A is not equal to 0, that B is also not equal to 0. Means A and B are non-singular matrix. Then that A into B is also not equal to 0. And that B into A is also not equal to 0. So that A is not equal to 0, that B is not equal to 0, then that A into B is also not equal to 0, that B into A is also not equal to 0. This is about theorem 2. If A and B are non-singular matrices of the same order, here same order, which is important, then A into B and B into A are also non-singular matrices of the same order. Now coming to theorem 3. What theorem 3 says us? The determinant of the product of matrices is equal to product of their respective determinants. Means when we take two matrices A and B, so first we are finding the product, then we are finding the determinant. So finding the product after finding the determinant, or finding individual determinants and then finding the product, both gives us same answer. The left side what we are doing? First we are multiplying A and B, then we are finding the determinant. Right side what we are doing? Individually finding the determinant, then finding the product. So however, we have the same answer. Here A and B are square matrices of same order. It is also important. So everywhere we are using square matrix and also the same order. These two conditions are important. Condition number 1, square matrices. Condition number 2, same order. Now, here we have an important point. So, for objective type, it is very, very important. If A is a non-singular matrix of order n, then a det adjoint of A. What we are finding? Adjoint of A and its determinant. So, determinant adjoint of A is nothing but det A power n minus 1. Here n indicates order. If it is order 3, so determinant A whole square. If it is order 4, determinant A whole cube. If it is square 2 by 2 order, det A power 1. So, det adjoint A is nothing but det A power n minus 1. Very important point is. Now finally we have theorem number 4. So very important theorem is also important theorem. What is that? A square matrix A is invertible. This word is very, very important. Invertible. Invertible means inverse is possible. Means inverse exists. A square matrix A is invertible if and only if A is non-singular matrix. As I told you, singular matrix means inverse does not exist. Non-singular matrix means inverse exists. So, the theorem 4 says that point. A square matrix A is invertible if and only if A is non-singular matrix. So whenever we have a non-singular matrix, we need to find inverse of a given matrix. Means inverse exists. Means the given matrix is invertible. Okay. So inverse possible. Then how to find the inverse? Here we have a formula of that. So how to find the inverse means A inverse is equal to 1 by det A into adjoint of A. So this is the formula for finding inverse. So our coming exercise is depending on this formula. A inverse is equal to 1 by det A into adjoint of A, where det A is not equal to 0. So det A is not equal to 0 means A is non-singular. So now you can have an idea why non-singular matrix inverse exists. See here det A, where the det A is there in denominator. If denominator gets 0, the answer is undefined, means infinite. So that is the reason inverse exists only for a non-singular matrix. So these are the three important theorems. Now based on these three concepts, we are going to have the further exercise. Let us see now how to find the inverse of a given square matrices, whether it is a 2 by 2 square matrix or 3 by 3 square matrix.